Electrophoresis is a technique of molecular separation that uses high electric current so that the charged proteins of DNA move and can be separated by size. This method is used in several analyses such as the following. DNA analysis. Specific sequences of DNA can be isolated and cloned, and they can be used for forensic investigations and paternity tests. Protein analysis. Making some tests, the level of some proteins in blood or in urine can be measured and compared to regular levels. Antibiotics analysis. This method is helpful to synthesize new antibiotics and also identify the bacteria that are resistant to them. Basin analysis. Basins can be purified, processed, and analyzed through electrophoresis. Some examples are influenza, hepatitis, and polio shots.
Electrophoresis does not work only for DNA or RNA but also for proteins. In the following table, examples of these procedures along with important specifications are shown. It is important to mention that there are a lot of protocols that can be followed, but only the most significant are shown.
The steps that should be followed to perform electrophoresis are: prepare the matrix, deciding if you are using polyacrylamide or agarose and the concentration you need depending on the size of the sample. Once this matrix is cooled and not jellified, add a colorant that will help you to identify the nucleic acid. Then you can pour the matrix into a previous setted mold of electrophoresis chamber with a comb. Now you have to wait till the matrix jellifies, and once it does, decide the volume and technique that will be followed to mix the DNA sample and the loading buffer, and mix them with a micropipette. Add the samples in the well. You can add a molecular weight marker, and this will help you to identify easily the size of the samples. Now you can add current to the chamber. This current will vary from protocol to protocol. We recommend to use 110 volts for 60 minutes.
Now current should pass through the chamber. This current will vary from protocol to protocol. It is recommended to use 110 volts for 60 minutes. Once the 60 minutes have passed, you will be able to visualize and document the results in the equipment of your preference.
There are some differences between DNA and RNA electrophoresis, such as previous deneutralization of the sample so that it doesn't have secondary structures. Addition of formaldehyde to the agarose gel maintains the RNA in its linear form. At low voltage, the rate of migration of RNA is proportional to the voltage applied. As the voltage is increased, the mobility of larger molecules increases differentially.
The results obtained through these electrophoresis trials can be observed in the following images. The markers in most cases ran as expected, which means that the gels were prepared appropriately. However, the human DNA and plasmid show distorted images in the gel. The three main groups in sample C, the plasmid, are three different isoforms that can be found depending on the cutting protocol and the enzymes used to cut it.
In sample A, there is only one clear line that is located between 300 and 500 base pairs. There is no way to obtain an accurate reading of the size of this sample with this specific marker, but it can be approximated to 400 base pairs.
Sample B is the human DNA, in which no results can be obtained due to the characteristics of the images. No lines are present in this sample. When comparing the three different concentrations of agarose in the gel and the displacement of DNA and the 1 kb marker, it can be concluded that the best concentration for this sample is 1% or 1.2% of agarose, since they are the ones where the best readings can be done. In the case of 2.4% agarose, there was not enough displacement, which does not allow any accurate reading. In the case of 0.6%, the displacement ran over the gel.
To know the quality of the sample of nucleic acids in the gel, we have to perform an analysis by observing results obtained in electrophoresis. To know the quality of the sample, it is enough to observe the bands obtained by electrophoresis. If bands are defined, means it's a good sample. However, if you look blurry or set, mean that there were certain compounds that may be contaminating the sample. The running buffer was selected because of the characteristics of the sample. Was used the TBE buffer 0.5x because the marker was 1 kilobases, and this buffer is used for separation of large DNA fragments, also having a greater revelation capacity compared to the TAE. The loading buffer used was run of an alcohol, as it provides density and allows the sample to fall into the well. Also, it serves as an agent that displays the run and works as an indicator to know when to stop the electrophoresis. Cyberscape was used because it is a dye that has a wide range of sensitivity, 1 to 5 nanograms. Also because it is less toxic and mutagenic than other dyes commonly used like ethidium bromide. It's carrying out the electrophoresis, the optimal voltage to the sample size used was 1 kilobase is 5 volts per centimeter, so the ideal conditions for shifting to the size of the gel was 20 centimeters had to be left running at 100 volts, but due to lack of time, it was allowed to run at 120 volts for 4 to 5 minutes. In our case, when using a higher optimal time, the DNA sample migrated faster also means that the bands are seen distorted. In case of using a lower voltage, we'll have slower mobility and can cause the bands to defeat.
And finally, our team's conclusion is the following.
The results obtained through this experimentation were unsatisfactory, since the samples ran through the gel and created expected images, yet the sample processing was not done correctly prior to electrophoresis. With the results obtained in the different gels, the best concentration of agarose for the samples is 1%. In this case, even if the right concentration of agarose is decided, the results are not optimal since the human DNA sample has been degraded by protein presence. This error can also be attributed to the high voltage used while running the samples.